A manufacturing plant upgrades to the fastest available technology. Robotic arms assemble units in fractions of a second, yet end-to-end delivery times remain stagnant. This occurs because of a specific misunderstanding about the nature of operational delay. Facilities often assume that because the machines are moving quickly, the overall system is moving quickly. To measure actual responsiveness, supply chains rely on lead time. Lead time is the total elapsed time between the initiation of a process and its ultimate completion. Lead time actively anchors all systemic planning and scheduling. It provides the temporal foundation for frameworks like Material Requirements Planning, or MRP, and SNOP. SNOP stands for Sales and Operations Planning, an integrated management process that aligns demand, supply, and financial goals. Without precise lead time parameters, critical calculations are mathematically impossible. You cannot determine a reliable safety stock level or set an accurate reorder point without knowing exactly how long resupply will take. This metric forms the foundational architecture of the operation. The time it takes a system to respond to demand dictates the customer service expectations you can reliably meet. Academically, lead time is the total elapsed duration from a process's starting trigger to its absolute conclusion. In supply chain operations, the clock starts when an order is placed. The clock stops only when the goods or services are physically received and fully ready for use. This measurement applies fractally. It exists at every level of the end-to-end supply chain network, taking on different forms depending on the specific domain being analyzed. This timeline shows procurement lead time, from purchase order to supplier delivery. Below is manufacturing lead time, from production order release to finished goods. Finally, customer order lead time, from buyer placement to physical receipt. These track physical movements, but there is also information lead time, which measures the unseen delays for data to flow and for decisions like forecast approvals to be finalized. Defining these exact intervals allows an operations manager to dissect the network. It is the only reliable way to isolate exactly where time is hemorrhaging. When diagnosing those time hemorrhages, operations managers often run into a persistent fallacy, the assumption that processing time makes up the majority of lead time. This chart deconstructs lead time into discrete components. We isolate processing and production first, often the only true value-added time. The remaining footprint is non-value-added: order processing, setup, transportation, and inspection. But the most significant component is queue time, which dominates the total delay. Because these idle queues dictate the timeline, lead times are rarely deterministic. They are highly variable and frequently much longer than anticipated. This queue-heavy structure reveals a hard truth about industrial engineering. Lead time is strongly influenced by the overall process design, not the speed of individual machines. Upgrading to high-speed robotic assembly arms rarely improves delivery dates for this reason. Faster machines simply push units into the next queue faster, where they sit idle. Meaningful lead time reduction requires engineering the empty spaces between the work. Shrinking the processing time yields minimal returns compared to eliminating the queues. The structure of this delay is governed by mathematical laws that directly impact a business's capital. The foundational principle connecting time and physical assets is Little's Law. It states a direct correlation. Longer lead times mandate higher work-in-progress inventory. The longer a unit takes to traverse the system, the more inventory must be held in the pipeline at any given moment to keep the system running. This creates a heavy physical and financial burden. Excess inventory ties up millions in working capital and rapidly consumes expensive facility space. Operations managers input these time estimates and demand forecasts into a Material Requirements Planning, or MRP, system. This software calculates the needed materials. The MRP system uses these specific time inputs to output exact reorder points and calculate safety stock minimums. A bloated lead time mathematically guarantees a bloated, capital-intensive inventory system. Beyond inflating inventory volume, extended lead times introduce a second governing dynamic regarding demand volatility. This graph illustrates the bullwhip effect. A minor fluctuation in customer demand at the end of the chain is mathematically magnified as the signal travels upstream. Extended lead times stretch the timeline, causing these demand waves to become violent and extreme. Operating on delayed, outdated signals, upstream nodes often panic. They wildly overcompensate for demand spikes they cannot accurately predict, ordering far more materials than the actual market requires. This creates a permanent trade-off. A highly efficient network is often brittle, while a highly responsive network requires expensive buffers to absorb these demand shocks. Ultimately, unchecked lead times function as a multiplier that exponentially amplifies chaos across the entire supply chain network. Today, these mathematical principles are currently colliding with modern macroeconomic constraints, threatening to expand lead times even further. Increasing global demand volatility makes establishing a deterministic timeline difficult. Predicting lead times is inherently more uncertain today than in previous decades. Global sourcing introduces longer physical distances between nodes. Shipping raw materials across oceans injects significantly higher risk variables into the lead time equation, from port congestion to geopolitical friction. The perceived financial savings of sourcing cheaper materials overseas must be weighed against the hidden mathematical costs of extended, unpredictable delays. This unpredictability actively breaks down internal lean initiatives. Lean is an operational methodology focused on minimizing waste. When lead times are volatile, lean fails, and evaluating supplier performance becomes nearly impossible. In a volatile global market, lead time reliability is a far more critical competitive advantage than the basic unit cost of your product. Today, cutting-edge supply chains are actively redesigning both their physical and digital network architectures to compress these inflated timelines. The primary physical solution is nearshoring. Nearshoring is the practice of transferring business operations and manufacturing to a nearby country. It drastically cuts transportation delays and mitigates geographic risk. Operations also strategically place decoupling points in the network. A decoupling point is a specific location where inventory is held to buffer against fluctuations. They act as shock absorbers against demand variability. On the information side, the solution is digital visibility. Implementing real-time ETAs and transparent data flow counters the delayed signals that trigger the bullwhip effect. Lead time is an end-to-end measurement where non-value-added waiting drastically outweighs actual processing. This interval of time directly dictates the required inventory levels through Little's Law and amplifies systemic chaos via the bullwhip effect. Mastering supply chain operations requires abandoning the illusion of machine speed. To successfully build a truly responsive network, operations managers have to step back and engineer the very architecture of time itself.